During spacecraft re-entry, extreme heat is generated due to atmospheric friction, which can reach temperatures over 1000 degrees Celsius. To protect the structure, thermal protection tiles, like those used on the space shuttle, are critical.
In this project, a single heat shield tile was modelled using a 1D heat conduction approach. The outer surface temperature is based on real NASA data, while the inner surface is assumed to be perfectly insulated. The goal is to simulate how heat travels through the tile during re-entry, and recommend a minimum tile thickness that ensures the spacecraft remains safe through the use of a graphical user interface. Starting with temperature profiles from the image-based data, 4 numerical methods were used to calculate how heat transfers through the tile. The explicit methods, forwards and DuFort-Frankel, calculate the next temperature directly from previous values, making them the least computationally demanding. The implicit methods, backwards differencing and Crank-Nicolson, solve a system of equations at each time step, making them unconditionally stable at large time steps. To extract temperature data from the re-entry profiles, an image analysis method was used. Since the desired curve was red, thresholding was used to identify pixels where the red value was high and both the green and blue were low. This allowed us to create a mask that highlighted only red parts of the image. The red pixels were then automatically extracted.
The automatic graph scanning compared to the manual method suggested in the brief enables more rapid and accurate acquisition of data from the images.
This three-dimensional graph shows temperature distribution for all spatial and time points. The temperature is generally the highest at the outer surface, where the heat is applied. The inner surface temperature gradually increases over time.
Two graphs, temperature versus time and temperature versus distance, are generated as perpendicular slices of the 3D plot. Multiple slices are compiled together as shown in the GUI, and a GIF is created to compare more slices without clutter.
Comparing the accuracy and stability of each method, simulations were run over a range of time steps. The inner surface temperature was plotted against the corresponding time step size.
A stable numerical method yields consistent results as time step increases. For accuracy, the results should align with those from smaller time steps, since these are assumed to be the most precise, though computationally intensive, as time step approaches 0.
The explicit methods, forward and DuFort-Frankel, become unstable with higher time steps.
The forward method is originally stable at small time steps, but quickly becomes unstable where p becomes greater than 0.5.
The DuFort-Frankel method shows similar behavior but remains stable at slightly larger time steps. In contrast, the backwards and Crank-Nicolson method are most accurate and stable, maintaining smooth, consistent results as time step increases.
To compare accuracy, the variance of inner surface temperature was calculated for both backwards and Crank-Nicolson methods. Backwards showed the lowest variance, making it the most stable, whilst Crank-Nicolson is theoretically more accurate. Backward proved more efficient here, delivering reliable results with lower computational cost.
A 10-second time step optimally balanced accuracy and efficiency, as high values offered no noticeable computational speed up.
Spatial resolution was tested by varying nodes from 10 to 500. Inner surface temperature changed with increasing steps showing initial inaccuracy. Beyond 200 steps, the curve stabilized, so 200 was chosen as the optimal balance between accuracy and efficiency.
Enhancements include the implementation of layered materials with editable thicknesses. This enhancement enables the accurate depiction of tiles with varying composition.
The user can choose different underside locations to undergo heat analysis. This feature improves the realism of simulations by allowing accurate representations of different underside locations.
The user is able to choose what method out of the 4 to use and how many layers to test and at what thicknesses. After providing a location on the shuttle's underside, the following results are represented: temperature against time for different spatial values, and temperature against distance for different time values.
The option to employ all 4 methods individually allows the user to directly compare their varying stability and accuracy characteristics.
Forward differencing exhibited the lowest stability. Consequently, when a user selects this method, the GUI's material referencing table also displays the minimum stable thickness for this tile's material layers.
The backwards differencing method demonstrated the highest stability and accuracy. When this option is chosen with a single material, a supporting graph appears illustrating the required tile thickness to maintain the inner surface temperature below 175 degrees Celsius. This temperature threshold is based on NASA's Orbital Thermal Protection System documentation.
The model's limitations include considering only one-dimensional heat transfer and using data from a single space shuttle re-entry, potentially requiring a safety factor for future missions with varying temperature distributions. Additionally, the assumption of a perfectly insulated inner boundary is unrealistic in space shuttle. The model assumes constant material properties, disregarding their variation with temperature. This simplification affects the predicted temperature at the insulated boundary.
The calculation method yields repeatable results across all 4 methods, indicating high accuracy and repeatability based on the model's assumptions. The recommended backwards differencing method is unconditionally stable and accurate in both time and space.
To conclude, it is recommended that our model should be run with the backwards differencing method with 200 spatial steps and time steps every 10 seconds. This gives a recommended thickness of 7.5 centimeters with the LI 900 tile material.